Why, hello, welcome. I'm Ashley. You stumbled upon my channel at Math with Ash, and as if it wasn't clear, we talk about math around here. So we're gonna do that. Today on the agenda, completing the square, a full tutorial, some examples, why you need it, and everything else you'd ever want to know about completing the square. So let's do it. Completing the square is a method to solve quadratics. When I mean solve quadratics, this is what we're talking about. So we have our y and our x-axis. Maybe you have a quadratic that looks something like this. When we're solving our quadratic, we're trying to find those roots, or namely, where our function intercepts the x-axis. And this is kind of along our y is equal to 0. So when we're looking at our equations, we're going to set that y equal to 0 and try and find what my x solutions are, right? Those roots, those solutions, they have a lot of different synonyms for names, but they all mean the same thing. So let's talk about those different forms that we have of the quadratic. So you can have this standard form, right? This is going to look like y is equal to ax squared plus bx plus c. So ways to solve this, remember when we're solving, we're having our y equal to 0. You might be able to put it into a factored form. You might be able to use the quadratic equation. Both of those will work to solve an equation that is in standard form. What if we have our quadratic in factored form? This kind of comes from that standard form if we're able to factor it, right? We'll have y is equal to, maybe we'll have a coefficient, we'll call it a, x minus my first root or solution, x minus my second root or solution. So sometimes we're able to factor a quadratic into this form. And this is really nice, right? Because when we're solving, remember we have our y is equal to 0. So if this factor right here is equal to 0, that's 0 times something else. So that's going to make this true. Therefore, we have a solution. Same thing for this right here, right? A number can't be equal to 0, so this is kind of irrelevant here. But that's where we get our solutions, right? If we have x minus r1, set that equal to 0, then we'll have x is equal to r1. So all of this to say that a factored form is really nice to tell us what our solutions are. But sometimes a standard equation cannot be factored. So sometimes it is a little bit easier to either do the quadratic, or if you don't feel like doing the quadratic, you can complete the square. And that's kind of where our vertex form comes into play. So our vertex form is going to look like y is equal to a times x minus h squared plus k. And this is called vertex form because we've got that h, k coordinate of a vertex. So that might appear right here in our quadratic. So what we're doing when we're completing the square is we're trying to kind of force a square to appear, this x minus h squared right here. So when we're thinking about solving it, we will have our y is equal to 0, and then we could probably move that k on the other side. We'll have this a times x minus h squared, and that's kind of the form that we're shooting for when we are trying to complete the square, because this is pretty simple to solve for x, right? We just use algebraic operations. So let's look how this works in an example. So the example I'm going to use is going to be x squared minus 8x plus 13 is equal to y, and we're trying to solve this equation, so I'm going to set it equal to 0, right? When our y is equal to 0, that's going to give us those solutions. So you'll notice in this equation that this is in our standard form, right? That ax squared plus bx plus c is equal to 0. And my a here is equal to 1. So when we're completing the square, if your a is not equal to 1, then it's an extra step, and we'll do an example like that a little bit further on. But let's go ahead and address how this works. So these are just the steps that I take. So what I'm first going to do is I'm going to do my x squared minus 8x, and we're going to move that 13 on the other side and replace it with something that we like a little bit better. So what's going to go in that spot? Well, remember we have our, I guess I'll write it up here, we have our ax squared plus bx plus c. We're going to take advantage of this b right here, and we, to force a perfect square to appear, are going to take these steps. So in these blanks, I'm going to add plus b over 2 squared. So my b is negative 8. What is negative 8 divided by 2 squared? That's going to be a negative 4. Negative 4 squared is going to give me a 16. And what I add to one side, I'm going to need to add to the other, right, to keep this a true expression. So that's kind of my formula, but what I'm actually going to do is write in the numbers for this example now. So I'm going to have that plus 16. My negative 13 plus 16 is just going to give me a positive 3. Okay, now it's time for me to actually create my perfect square. So what we have is a perfect square right here, but we want to put it in that kind of factored-ish form. So this time we're going to have x and then our blank squared, and that's going to be equal to 3. And in this blank, what I'm going to put is my original b divided by 2. So what is my b divided by 2? It's going to be my minus 4 squared. And I'm going to have that equal to 3. So let's just check that this makes sense, right? So let's do a quick check to kind of see where that comes from and what we're really doing. So x minus 4 squared is the same thing as x minus 4 times x minus 4. And if we multiply that out using FOIL, first, outer, inner, last, first term's x squared, outer term's minus 4x, inner minus 4x plus 16, combine those like terms and we'll get x squared minus 8x plus 16. That looks pretty familiar, right? So all that we're really doing is putting a number right here so that it'll create a trinomial that I can make into my perfect square. So we're kind of forcing a number to be right here and then kind of putting it in this factored form that we like, this perfect square. Now, this is just an equation, right? And I can easily solve this equation for x. Right, so my whole goal is to get everything away from x now. So what would I want to do first? I think that I would want to take the square root of both sides, right? Get rid of that squared. So we have x minus 4 is equal to plus or minus root 3, right? And last thing I need to do is add that 4 on both sides. So I get x is equal to 4 plus or minus root 3. So that is how you complete the square. You take your constant, move it on the other side, and then leave a little gap and force what you want to be there by what you do to one side, you do to the other. That's why we're allowed to do that. It makes our perfect square that we want, and then we're able to kind of use algebra to solve easily. So that's really the crux of it. Let's do one more example where we have our a, our leading coefficient, not equal to 1, because there's just one extra step that we need to remember. So our example where a is not equal to 1 is going to look something like this. So 2x minus 4x minus 5 is equal to 0. And you'll notice in this case that there's not something that I can easily factor out of all 3 of my terms, right? If that was the case, I would be able to maybe factor that out and then go from there, use my regular completing the square rules, but there's not something that I can factor out of all 3 of those. So I am going to go ahead with my completing the square rules. So like before, we're going to scooch that 5 on my other side by just adding. And now what I'm going to do is factor out something out of both of these terms so that my a right here will become 1. This is kind of a nice example. You can see that we'll factor the 2 out of there and my a will become 1. But even if it's not a nice example, you always need to just factor out what number is right here, right? Because that'll leave you with a 1 in my parentheses. Okay, I'm going to leave my gap per usual, and this is still equal to 5, right? We haven't changed the value of anything. We're just factoring that out. And we're going to use our same rules as before. So we're going to think about my b divided by 2 squared to put right here. So negative 2 divided by 2 is a negative 1. A negative 1 squared is a plus 1. And what we do to one side, we have to do to the other. But what are we really adding to both sides? Well, it's not a plus 1 because if we were to distribute that 2 out, we're actually adding a 2 times 1, a plus 2 to my left side. So I need to actually add a plus 2 to my right side also. Okay, now we're going to make it into our perfect squared. So that's going to be my b divided by 2 beside my x. So minus 1 squared. That's going to be equal to 5 plus 2, which we all know is 7. Okay, this becomes an algebraic problem that I can go through and easily solve. So getting the x by itself, I want to divide by 2 on both sides. And then I'm going to want to square that, right? Get rid of that squared. So I have plus or minus root 7 over 2. Last thing to get the x by itself, I'm going to want to add a 1 to both sides. And there we have it. X is equal to 1 plus or minus root
7/2. So this is our example where a is not equal to 1, and there's not something that we can easily factor out of all three of these for my a to become 1. And then this was our first example. So this is how I complete the square. I hope this video had some useful tips. Yeah, if there's a topic that you want to see, definitely drop it in the comments below. I'm open to all kinds of ideas, and thanks for tuning in. I love all of you.